refer to all those three interchangeably depending on the question on the exam, so you have to remember that. You also have to remember that these specifically target these things for breakdown. Now, normally during exercise, right, the normal response to training is when we first do a new exercise stimulus, because it's so new, there's a large degree of inflammation or an inflammatory response to that new stimulus, okay? There's also not that as specific of an anabolic response. What they've shown is that the more training you do, specifically with resistance training, the more specific the anabolic signaling response gets, and also the less intense the inflammatory response gets. So if we think about this, how often do you hear people say, I had a great workout yesterday, I'm so sore, right? It's like, oh, I didn't have a great workout. Oh, I don't really feel it, right? I don't. The next day, I feel like it's okay, right? I'm not really feeling the soreness. The body's natural response to a new training stimulus is, if it's new and difficult, there will be an inflammatory response because it's likely a new and difficult stimulus, right? So we've probably broken down a lot of tissues, a lot of muscle fibers, a lot of proteins damage. We need to regenerate that tissue because we're probably not accustomed to that stimulus. So initially with a new stimulus, there's likely to be a lot of muscle damage or inflammation. But the normal response is that your muscles adapt, they get more resilient, and therefore the muscles don't become as inflamed after the exercise stimulus anymore, right? When someone's untrained, you could walk around like a stiff cardboard, right? You're so sore from doing a workout, right? But the more training you're doing, you notice that the soreness, the DOMS doesn't get to you as much, okay? So that is a natural process of adaptation. The problem is when people are chronically chasing that soreness as a sign of a good or effective workout, they're actually working against their physiological process, right? Because you don't want to be sore, right? Inflammation and soreness actually is a catabolic event, right? It can signal regeneration, but when it's too much, it overrides anabolism, right? So if someone's chronically chasing soreness as an indicator of a good workout or workout quality, that's the wrong way to go about it, right? If anything, it's likely that when you start a new training program, you should expect some kind of soreness and DOMS, right? But as you proceed through that training phase over a few months, you can be pretty assured that you're getting the adequate training stimulus, even though the inflammation and soreness is going away, because that is, you're adapting to that stimulus. And then maybe after that 3-month phase, you start a new exercises, new loading, new volumes, and then you'll be sore again. It's a new stimulus and so on and so forth, right? So the normal response to training is that anabolic factors go up, right, or are maintained. Inflammation and soreness goes down. That is the normal response. And we see that after just 3 workouts, right, MathBox at rest is less than the initial exercise session response. Same thing with MRF, okay? Same thing with TNF alpha, this anti-inflammatory cytokine, right? It actually goes down following repeated bouts of training, right? After in recovery, right? This cytokine response becomes less. So what happens with overreaching or overtraining in humans inside skeletal muscle? Unfortunately, there's not a whole ton of research looking at what goes on in the muscle in humans with excessive exercise or overtraining, because one, what athletes are gonna actually want to get stabbed and do bad training just to see what happens, right? And who knows when you recover, right? Overtraining is your decreased performance that's unexplained, and then even with recovery, you don't rebound, right? You don't recover. So who would voluntarily sign up for that? So part of why we don't know a lot about the etiology and development and the avoidance of overtraining at the molecular level is because it's so hard to study, right? Muscle responses in the muscle are so hard to study as it is, and now you have specifically athletes or overtraining. It's so niche, it's hard to know. But we are able to study animal models with excessive exercise, and it can give us an idea of what really intense exercise or insufficient recovery might do to the muscle in certain cases, right? Without actually using humans. So in this study, they had mice, and they had a resistance training program, so they had them wear a weight vest, and unfortunately, this isn't necessarily how humans would lift, right? In order for them to make sure they did a repetition, they had the cylinder filled with water, and they had to jump, literally do a squat and jump above the water to keep their head over water to stay alive, right? So that was their training stimulus. Are humans every time they do a squat, is it gonna be life or death? Probably not, right? So I don't necessarily think the total like workout stimulus is like equivalent to what would be in humans, but it does give us a really finite look at what is really truly excessive exercise, right? The exercise is too much, but also it's a stressful environment. Every time they exercise, it is literally life or death. But, you know, the other thing is like, okay, you know, how do you get rats to train? You can electrically shock them, right? And you know, that's also not great, but it's part of science, and that's how they do it. At the end of the day, to study this, they'd have to kill the animals anyway, right? So, you know, I mean to be like, you know, rude about that, but in animal science, they sacrifice them humanely, right? So there is a process of going through that. But the reason why we know so much about lots of diseases and we're able to cure diseases is because we do research on animals, right? Right? And the only way we can train them to study this phenomena is to genetically engineer them, study them, and then we have to sacrifice them to get the information, right? So it sucks. It's like, oh, who would train like that? Those poor mice. But ultimately, whether they did this kind of workout or they were just overfed to obesity and study obesity, they overfed them to death, they would be sacrificed anyway, right? So ultimately, this does give us a good idea of how excessive exercise or stressful exercise with not enough recovery would affect muscle physiology. So these animals were squatting, they were jumping, lifting overloaded over 12 weeks. In a mouse's lifetime, that's the equivalent of years. So this is like doing overtraining exercise for years, okay? So what happened to their muscle? If we look at, this is the control, the sedentary mice. These sedentary mice, this is their muscle size. The mice that actually lifted weights, their muscles actually atrophied. Have you ever heard of this in humans? Right. Most times, when humans lift weights, practically, either the muscles don't change in size or they get bigger. You almost never see muscles actually atrophying in humans, right? So what does this say? Would this happen in humans? Probably not, right? I probably don't think, you know, maybe if a human was doing that for years, maybe, but you know, physiologically, I think there's going to be a lot of things that would prevent that. You'd probably actually maybe just stop lifting at that point versus too much. But what it does show is that, you know, even though, like when you lift weights, mTOR is turned on, protein synthesis turns on, satellite cells get activated. All these things help the muscle recover and get bigger from lifting weights. This is tried and true. We know this happens. So what's interesting is that here they have mice lift weights, and what do we see? When there's insufficient recovery or too much exercise, you get the opposite effect. Muscles do not increase in size. In fact, muscles atrophy, right? So it does show that just because you lift weights doesn't mean that it's going to cause growth, right? And in fact, if there's not enough recovery or it's too hard of an exercise, maybe that results in atrophy. At least it shows this in animal models. So you might suggest, well, why did the muscles atrophy? Well, they looked at proteins in the muscle related to atrophy and anabolism. MathBox, it goes up in the group that did the training, the excessive exercise, okay? IGF-1, insulin-like growth factor, is a growth factor. Like I said, remember I said muscles contract, they release a protein, tells them to grow, right? IGF-1 is similar to that. It not released from the muscle cells itself, it can be synthesized, but ultimately insulin-like growth factor tells the muscles to grow. Satellite cells can be turned on by insulin-like growth factor as well, right? So what do we see? In the group that was training, the amount of insulin-like growth factor decreased. Also, MyoD decreased. Myogenin decreased. Normally, what happens to these proteins after exercise? They go up. What do we see when you overtrain animals or you do excessive exercise and insufficient recovery? We see that MyoD and myogenin go down. And this kind of connects back to that previous slide. Remember, MathBox inhibits MyoD. Why? Because MathBox can target MyoD for degradation. And what do we see? In this study, MathBox goes up, MyoD goes down. Right? So there is that connection there. Right? There was an increase in these atrophy proteins that resulted in muscles atrophying. Why? Because at least partly, the degradation goes up, but also there's the inhibition of these anabolic. There's 3 anabolic factors here: IGF-1, MyoD, and myogenin. All 3 of these decreased. Right? MathBox, the catabolic one, increased. So there is this switch between the environmental state in the recovery process, when there's not enough recovery or too hard of exercise. Yes, Mark?
This could speak maybe wrong, but could you get like lower IGF because it's just this constant exercise, like constant stimulus?
Possibly, yeah. You know, I mean, part of we'll talk about in the next few slides, is part of maybe why there's a decrease in some of these anabolic proteins is because the process of protein synthesis is partly interrupted. So that might even be part of it, right? But we're still kind of learning about that. So if we see here, so that study was like 12 weeks long, very excessive, right? It was a lot, okay? Maybe not totally applicable to humans, but we do see that as a proof of principle, there is an effect there of, you know, this interference in adaptation when there's too hard or too difficult of an exercise for too long. So in this study, what they wanted to do was look at what about the length of the recovery period. So they had mice and they had them do 3 training bouts. The only thing that differed was that one group, the training bouts were spread out between 3 days. The other group, they had 1 training bout per day. And the other group, they trained every 8 hours. So it was 3 workouts in one day, okay? Same number of workouts, the only thing that differed was how much recovery you got in between those workouts, okay? So they looked at some anabolic signaling proteins and protein synthesis, and what they see, P70, which we know is activated by mTOR. We know the mTOR pathway is important for protein synthesis. We see that when you have the longest recovery sessions in between trainings, you have the lowest increase in P70 activation. If you had 24 hours between training sessions, it was P70 was higher, and if you had just 8 hours of recovery between training sessions, you had the highest increase in P70 activation. So if you look at this, you might say, wow, should I be getting even less rest and recovery between training, right? Signaling is better, signaling is higher. I should be getting less rest and recovery between training. I should be training more, okay? But in reality, when they actually looked at protein synthesis, the groups that had the longest recovery between training bouts actually had the actual highest increase in protein synthesis, right? 24 hours, also a very high increase in protein synthesis. The only group that did not increase protein synthesis significantly was the shortest recovery group. Right? What is the purpose of the mTOR pathway and P70? What does it do?
To activate protein synthesis.
Yeah, it helps assemble a ribosome, and that ribosome then produces protein synthesis, right? It's part of initiating and controlling protein synthesis. So what's interesting here is that now we see when there's an imbalance between the exercise and the amount of recovery, we see that there's this disconnect between the anabolic signaling and the purpose of that anabolic signaling, protein synthesis, right? The mTOR pathway's purpose, when this gets turned on, it's a signal to tell the muscle to increase protein synthesis. But what ends up happening is that when there's not enough rest, that signal turns on and accumulates, but when you exercise too soon, it interrupts the process of protein synthesis, okay? So what this would suggest is that, yeah, not having enough rest between training bouts might increase anabolic signaling, but it might be detrimental to actually producing those proteins from protein synthesis, right? This is why having adequate rest in between training sessions is so important, right? Myostatin decreases for about 3 days post-exercise. The decrease in myostatin allows anabolic signaling and satellite cells and all those other factors to regenerate the tissue, to build, to make those adaptations occur. Okay, so here it kind of makes sense. When there's enough rest in between sessions, protein synthesis and anabolism can recover, it can go up. But when you start to recover and then do another session again while you're starting to recover, it pretty much stops that process and you have to start all over again, right? It's like, oh, I'm getting ready to start this paper, and then, oh, God, I gotta go do something, right? Okay, you go do it, and then you go start again, you maybe wrote another line or two, then, oh, I get interrupted again, you have to go back. You never actually complete the assignment because you keep getting interrupted, right? This is kind of what's happening in the muscle. When you interrupt that recovery with more exercise, and you haven't fully recovered, you're interrupting that recovery process. You're basically starting over again, all right? So this study is just looking at protein synthesis and anabolic signaling. You might say again, right, is signaling indicative of long-term adaptations? not necessarily here, we're looking at protein synthesis, so at least short term, yes, this makes sense, this is true for this instance, but this doesn't mean that this is gonna blunt adaptations long term, right? So what this group ended up doing, instead of a short term study of only 3 sessions, they then did a long term study where they trained for, I think, 10 or 12 weeks, okay? Same rest intervals. One group had 3 days of rest between trainings, the other had 1 day of rest between training, the other group only had 8 hours of rest between training, okay? And they trained them for, I don't know how many weeks, a long time. What did they see? The group that had the longest rest, muscle fibers increased. The group that had 24 hours of rest, muscle fibers increased their size. The group that did not have the longest rest, right, the group that only had 8 hours of rest in between training, the shortest recovery group, similar to that other study, muscle fiber size atrophied, right? So here's another instance where when there's not adequate rest between training sessions, or it's too hard of an exercise, here's one more study that shows muscles will atrophy, okay? Are we gonna see atrophy in humans? Probably not, right? This is a 10 or 12 week training study in mice. That's like the equivalent of years. But if we know if there's enough rest, muscles will grow. That is typical of what we see in humans and of good training. But when there's not enough rest, muscle fibers atrophy, right? So again, another instance of this opposite effect of if loading increases size, well, heavy loading with insufficient rest prevents the increase, or in some cases decreases, right? So you might ask yourself, okay, protein synthesis is lowest with the shortest recovery group, and if you do the shortest recovery over many weeks, then it actually does accumulate into muscle fibers atrophying. So now we're seeing this connection between, yes, the signaling builds up, but we're interrupting the protein synthetic process because we're doing more exercise. If you're not accumulating protein synthesis, let's keep stopping, then muscles don't grow, right? But that doesn't explain why the muscles are getting smaller, right? Muscles not growing versus muscles getting smaller means that one is just not getting bigger, the other, they're losing something, right? So even though this says muscles fibers get smaller, the protein synthesis not increasing significantly, right, is not explaining why the fibers are not getting, they're not explaining why fibers are getting smaller. If anything, synthesis is just the same or slightly higher, you would say the fibers should stay the same, but we're seeing that they go down. So why are the fibers atrophying with insufficient recovery? Because when you look at markers inside the muscle related to protein breakdown and ubiquination, we see that when you have 3 days of recovery, right, proteins are still ubiquinated, okay? The part of recovery, of adaptation, is that when you do a stimulus, the muscle fibers, they break. It's a heavy load. There's muscle damage. You can't just leave damaged proteins and damaged fibers and damaged cells in the cell. You have to replace and remove them, right? And you have to regenerate those tissues and cells. So if you look at it and say, oh, proteins were ubiquinated even with the 3-day recovery group, but protein breakdown is a normal part of recovery, right? If you wanted to rebuild this building, right, significant remodels, what would you have to do? You have to break down some walls, and you can't just leave the debris there. You've got to get rid of it, okay? So this is what happens. A lot of times, people will focus, they see this study and that study results, and you see these pundits or these blogs online, like, oh, this research shows this, and this research shows this, and a lot of research is focusing on anabolism, right? Getting bigger, protein synthesis, right? Anabolic pathways. But in reality, just because ubiquination or protein breakdown goes up, it doesn't mean it's a bad thing. In fact, it's part of a normal process of recovery. They've shown that if you inhibit protein breakdown, the muscle fibers don't regenerate the same way, right? Yes, they can get bigger, but the functionality of those fibers are not equivalent, right? They're not adequate. So this is normal training. This is part of normal adaptation. We see is that when you have 72 hours or 24 hours of recovery between trainings, you have similar amounts of ubiquination, but the shortest recovery group had significantly higher amounts of ubiquination of proteins. Okay? If more proteins are being ubiquinated, what does that mean?
More proteins are being
more proteins are being tagged for breakdown, okay? And if we can look at that, Atrogen 1, right? It's also called MathBox, right? Atrogen 1 gene expression, no change in the longest recovery, actually goes down after 24 hours in their recovery group. The shortest recovery group, 3 times as high. What about Murph? Again, no change, decrease, 3 times as high when you have the shortest recovery, right? So why do muscle fibers in mice and in animal models, what do we see about excessive exercise with insufficient recovery? At least in animal models, it says there might be an increase in anabolic signaling, but ultimately the shortest recovery results in impaired adaptation. Right? What kind of adaptations? Well, at least for growth, muscle fibers are not growing. They're actually atrophying. You might ask yourself, why? Because there's an increase in Murph and MathBox, right? The increase in those proteins, tag more proteins to be ubiquitinated, results in more protein breakdown. So when you have the absence of protein synthesis and an increase in protein breakdown, overall, what's the effect? If synthesis is not changing and breakdown is going up,
You get smaller.
fibers get smaller, right? Overall, it's negative, it's net negative, right? So like if protein synthesis was +1 and then protein breakdown was -3, the difference is -2, right? You still lost even though there was an anabolic response. There was an anabolic P70 response. There was a small increase in protein synthesis, but ultimately those proteins keep getting broken down, keep getting interrupted, lack of protein synthesis eventually results in muscles atrophying. Now, would we see this in humans? Honestly, I don't think we would. I don't think we would see this degree on this variable in humans. I don't think if you have humans do resistance training hard all the time, that muscles would eventually atrophy. I just don't see that stimulus being possible in humans. But the data probably suggests maybe in some way it prevents adaptations from optimally happening, right? So maybe the fibers aren't getting bigger, but maybe the fibers are just not adapting, right? Maybe the fibers aren't getting smaller, maybe the strength isn't going down significantly, but maybe you're just not getting bigger, you're not getting faster, maybe the aerobic capacity is starting to blunt or not get better. Kind of all goes back to Hans Selye's GAS, right? When there's too high of a stimulus and there's either not enough recovery or you don't recover adequately enough, it prevents supercompensation. So in this case, I think maybe in humans, we might actually end up just being no adaptations. And if that continues, maybe over time, we just decrease performance. And over time, it's not just performance goes down. With overtraining, there's mood changes. You get depressed, you get tired, you have poor motivation to train, right? So I think in humans, like unlike these animal studies where you force the animals to exercise and eventually they atrophy, in humans what's probably more likely, you just have no motivation to train, you just stop lifting, right? And that's actually one of the hypotheses around overtraining too, is like, why does motivation and desire to train go down in overtrained athletes? Well, one, they're depressed, right? And their mood is disturbed, but they hypothesize that if it's the exercise that's too much and excessive, maybe it's the body's natural way of telling yourself to stop exercising. This is too much exercise, so the change in behavior and attitudes results your mood to not want to train, right? So maybe that's kind of this like mechanism to try to get your body to stop training because it is too much. That's why you're overtraining, because you exercise too much, right? But ultimately, if we're recreationally trained people, we can choose not to train. We can take a month off, a week off. We can choose never to train again if we don't want to. But in cases where you're an athlete, you're part of sports, right? If athletics or training or something is part of your income or livelihood, or like if you're a war soldier, right, and you have to, performance is optimal, you're in like environment that's not great, right, for nutrition and performance and recovery, and you have to continue, well then you can't just not train, you have to continue on, and maybe that's where this overtraining syndrome really solidifies, right? But ultimately, there's not a huge lot of data of this in humans. What we now have, at least at molecular level, is a few studies in humans, a few studies in animals, kind of leads to maybe there's this imbalance between anabolic and catabolic environments in the muscle and recovery, but at the end of the day, we need more research to really understand why this is happening exactly, right? And earlier when I said protein synthesis was blunted, or it's like the smallest increase with the shortest recovery group, eventually it results in atrophy. You might think, well, why does protein synthesis not continue, right? The signaling is high, P70 is really high. Why doesn't you just continue to go through protein synthesis? Because remember, when you exercise itself, is it catabolic or anabolic? Catabolic. You're breaking down glycogen, you're breaking down lipids. Contraction damages muscle fiber integrity. There is muscle damage. It is an overall catabolic environment. But once you stop exercising, those responses then signal an anabolic state in recovery, okay? So when you exercise, protein synthesis stops, okay? Why? Because literally the ribosomes, as they line up on an mRNA, when you start contracting, it actually causes the ribosomes to bump into each other, and that tells them to disassociate, right? So if the ribosomes disassociate because you started to contract again, have you completed protein synthesis and recovery? No, right? So that's why protein synthesis is not the highest in the shortest recovery group, even though mTOR is the highest. Because when you start contracting again, the ribosomes disassociate because you're starting to exercise. Remember, you can't be anabolic and catabolic at the same time. You're not making and breaking it. You are either breaking things down or you are making things. Right, so it wouldn't make sense for us to be increasing protein synthesis during exercise because we need that energy for exercise. Right? And one way is, how does the body know? When you start contracting, the ribosomes will disassociate and stop the protein synthetic response, which maybe explains why there was low protein synthesis. And if you're doing that every 8 hours, you're not getting the increase in fiber size. You're actually getting a loss. Does that make sense? Cool. So that's that on the exam for that material. Next, we'll talk a little bit about nutrition, some components of nutrition like protein and carbohydrates and a little bit of alcohol. Right. So when we think about protein requirement needs for athletes, okay, there's a couple recommendations that kind of depends on your athletic or your physical activity levels. Right now, the RDA, the recommended daily allowance for sedentary people, is 0.8 grams per kilogram of body mass, okay? So this is relatively low, my suggestion. Okay, I mean, it's adequate, but I think most people are, if they're exercising, they for sure would need some more, which is why if you look at even someone who's doing endurance exercise, there's gonna be an increase in their protein requirement needs, okay? They suggest if it's light exercise, maybe not an increase, but I think more data would suggest more recently some meta-analyses that, yeah, maybe if you're doing endurance exercise, you might need a little bit more, right? The needs might go up slightly. In any case, the protein requirement needs go up for sure when you're doing strength training, okay? Because strength training is about building the muscle up, okay? It's increasing muscular strength, increasing muscle size. Muscles are made of proteins. The only way that you're going to rebuild those tissues is to consume more protein, okay? So, if you're just maintaining an adaptation, maintaining strength, the recommendations are 0.9 grams per kilogram of body mass. But if you're specifically looking to increase muscle mass, the recommendations are higher. So 1.2 to 1.7 grams per kilogram of body mass, okay? In general, they recommend for athletes to take around 1.5 grams per kilogram of body mass. It kind of depends on your training goals. So they have shown like 1.5 is adequate, right? You could go up to 2, and that is, depending on training status and the workout stimulus and the training program, maybe that's even better. But taking more than 2 or 3, right? It's good, but it's not required, right? They've shown that you can take up to 3 grams per kilogram of body mass of protein per day, and there's no detrimental effect on kidney health. Okay, so I'm sure that you've maybe heard myths about, high protein intake damages your kidneys, it damages your health, right? If you have healthy kidneys, if you're a healthy individual already, there is no data to support that high protein intakes are detrimental to your health in any way, okay? And in some cases, like if you're on a strict diet, having higher protein intake might even be better for maintaining muscle mass during a caloric deficit. So the higher protein intake is definitely supported. But the thing is, not everybody needs such a high protein intake because it depends on what your goals are, right? A typical Western diet is actually, in general, already pretty high in proteins, right? A Western diet, most people are getting at least the RDA of their protein requirements in their average diet. Now, obviously, if you want to maximize that effect, you could eat some more, right? And that would likely increase your protein intake. But if you're specifically training for maximum size or maximum strength or highly anaerobic adaptations, then you probably might want to include a supplement in there because you, at the end of the day, might be eating a lot of food and maybe that's not sustainable. Maybe supplements are the way to go, okay? But for sure, if you're training and you're trying to enhance resistance training adaptations, higher protein intake is highly recommended. Now, does it matter when you take the protein? We do know that protein synthesis is elevated after a workout, okay? During exercise, we're catabolic, protein synthesis is off. After exercise, the ribosomes assemble, you go through protein synthesis and recover, okay? Now, in those early studies, when you're looking at protein synthesis and how much protein you should take, most of those studies were looking at protein synthesis in the first hour or hour and a half of training, okay? Within of training. So what they saw was that protein synthesis was elevated within the first hour of exercise. So, and also the amino acids from that, when you took the protein and you took the supplement post-exercise, the amino acids were available within half an hour to 45 minutes. So this hypothesis or this recommendation came that there was this anabolic window, right? Has anybody heard of the anabolic window before? And say when you're training, you have so much time to get your protein after exercise, and after that, the anabolic signals are diminished, right? It goes away. You've lost it. You've missed it. The train's gone by. What we know now is like, yes, the anabolic factors are elevated post-exercise, but it doesn't need to be within the 45 minutes or an hour to get your protein. In fact, even though protein synthesis is elevated within 1 hour post-exercise, the muscle is still having elevated protein synthesis even 3 to 4 hours post-exercise, right? So it's really more like a window, like a flexible window, right? It's like a sliding door. There's a wider range to get your protein intake after exercise than what we had previously thought, okay? So, yes, Mark?
Would that change for carbohydrate?
Yes, for carbohydrates, you do want to get your carbs as close to the exercise session as possible because even though with protein synthesis, the ribosomes are assembled, the ribosomes are working to incorporate those amino acids and make the proteins. However, with carbohydrates and glycogen resynthesis, part of what helps glycogen get into the muscle is the fact that you have these GLUT4s that are activated and sensitive to it. So those are activated and sensitive because you've contracted the muscle. Also, your insulin sensitivity is high because you're more sensitive to having insulin because you have exercised and because you've decreased the amount of glycogen in the muscle, glycogen synthase is elevated in that case as well, okay? So all of those factors initially cause the resynthesis of glycogen to be really high within the first few hours post-exercise. They have shown that if you get your carbohydrates, 3, 6, 7 hours post-exercise, you delay that carbohydrate intake, then because glycogen synthase is not as active, because the GLUT4s have now gone back to their vesicles, you're not able to actually bring that glucose in and resynthesize glycogen to the same extent as if you had it earlier, right? So a lot of the mechanisms about timing and the need to get your nutrients very quickly for carbohydrates and glycogen resynthesis, that's very well supported. You do need to get those carbs really as soon as possible. The sooner the better. With protein, there's a longer period of time that you can wait and still have pretty effective protein synthesis and adaptations to exercise, right? So for protein, it's not as essential to get it as right away. Carbohydrates, it is. Right? The other thing to keep in mind is that most people are not doing resistance training totally fasted. So a lot of these research studies where they initially studied protein synthesis was people show up to the lab, totally fasted, and then they do the exercise, then they take the protein, and then they see what the response is. realistically, most people, unless you're exercising first thing in the morning, most people, if you're doing an afternoon workout, you've had breakfast, maybe you've had lunch, maybe you had a pre-workout, meal, or if you're exercising at night, you've had maybe 3 meals, and so if you've eaten, the amino acids are in your circulation already. They've shown that if you have adequate protein in the diet as a whole, it doesn't matter whether you get the protein pre-exercise or post-exercise. So if you're fed versus not, it doesn't matter, right? The protein's already in circulation. But if you have not eaten, then getting the protein post-exercise within a few hours is going to be important, right? But you can't just not eat, exercise, not eat, and then go 4 hours later and have a meal. That wouldn't optimize the adaptation because you've gone too long without amino acids in your system, and that's kind of missed the boat on that, all right? So timing is important depending on your protein needs, your eating strategies, and things like that. Now the protein source is also important, okay? Protein can be derived from whey, right? Whey is a byproduct of milk. Both casein and whey are byproducts of milk. Whey protein is rapidly absorbed. So you take whey protein, it gets into the circulation very, very quickly, okay, within an hour. Casein protein is digested at a much slower rate, okay? So it's gonna get into your system a little slower, but it's gonna cause more sustained levels or presence of amino acids in circulation. Whereas whey protein, you consume it, right? Amino acid circulations are low, you consume whey protein, they go peaks, go high, and then it goes down over time, right? Within a couple hours. So we know that it's more rapidly digested with whey protein. So whey protein might be the kind of protein you take post-exercise because it's gonna get into your system very quickly, kind of optimize that response. Casein protein, because it's slower digesting, you might want to take that maybe pre-sleep. We'll talk a little bit about pre-sleep strategies and feeding a little bit later. Milk is this good post-exercise drink. Do you guys remember the milk campaigns? Right, Got Milk? Remember that? I think way back in middle school, everybody's drinking milk. Everybody had milk mustaches, right? Now we got a real mustache, not a milk mustache, right? It's black, but it's not white. But anyway, really proud of my mustache now. That's why I haven't shaved because I'm too busy. But also I like my mustache. So milk is a good post-exercise drink. It's recommended because it has some proteins. It's chocolate milk. It has some sugars. So there's a lot of funding by dairy research groups and dairy funding to see what is the effect of dairy, and milk is dairy, on exercise adaptation. So we got to understand a lot about protein supplementation and the effects of that on exercise with resistance training, aerobic training, so on and so forth, because a lot of it was funded through some research through dairy, all right? And that's not a bad thing, but just because milk increases protein synthesis post-exercise doesn't mean it's the best source of protein post-exercise, right? So if you take a glass of milk, you're probably getting around 7 or 8 grams of protein, depending on how much milk you're consuming, compared to whey protein. You can get 2, 3, or 4 times that, depending on how much. It's much more easily accessible, right, in a smaller volume. So if you need protein really quickly and you don't have a supplement, then sure, you can go for milk, and that's good and it's adequate. But I would say there's post-exercise is probably more optimal sources of protein to replenish and refuel besides milk, right? Not a bad thing, it's an option, but if you want to optimize adaptations, then maybe we should go with something else, but it's a source you could use. So how much protein do you need? It kind of depends on the workout you're doing, right? Current research suggests 25 grams of proteins is enough, but more recent research suggests that if you're doing whole body type workouts, activating more muscle mass, then 40 grams is better, okay? So the recommendation of how much protein you should take post-exercise depends on the workout, the stimulus you're performing, okay? But initially these 25 grams came from the fact that a lot of research was only done on one body part, right? And then they just said, well, what about if you did more body parts or more volume being activated in the body, and it led to more knowledge, right? So this study is interesting because they had the same individuals come back on 3 different occasions, okay? And they performed the same resistance exercise stimulus. Each condition, they consumed 80 grams of protein in the 12-hour recovery period, right? However, how that protein was distributed and the amount differed between the three conditions. So at the end of 12 hours, they all consumed up to 80 grams of protein. The only thing that differed was that in the bolus condition, they took 40 grams once, and then again 6 hours later. Right? The intermediate condition, they took 20 grams, right, 4 times, so it's spread out by 3 hours each. And then they had a really small amount, they called the pulse condition, where they took 10 grams taken 8 times over a 12-hour period, right? So bolus means big, a lot, right? Intermediate is intermediate, and then pulse is kind of like a pulse wave, right? It's smaller but more frequent, okay? They wanted to see how does the protein synthetic response post-exercise differ between the different amounts, the different distributions of proteins in that recovery period. And what they saw was that all 3 workouts increased protein synthesis over the 12-hour period in recovery, okay? So all 3 increased protein synthesis, but the intermediate distribution actually resulted in the greatest overall increase in 12 hours, okay? So when you look at some of these graphs and it says myofibrillar FSR, right? We've been talking all semester about protein synthesis. But when muscles make proteins in protein synthesis, you can make proteins in the myofibrils, or you can make proteins that are in the cytoplasm, right? You can, mTOR is a protein in the cytoplasm, myosin is a protein in the myofibrils, right? When we think about hypertrophy and muscles growing, we're usually assuming that the hypertrophy comes from myofibrillar hypertrophy, right? Myofibrillar protein synthesis. So when you see FSR, fractional synthesis rate, this is meaning that this is the fraction of protein synthesis that is coming from making myofibrillar proteins, right? So if myofibrillar protein synthesis goes up, long term, would that result in more growth and more strength?
Yeah.
Potentially, yes, right? Because if you keep making those myofibrils, you're making more sarcomeres, eventually you'd have bigger, stronger fibers. So what we see here is that all 3 conditions increase myofibrillar synthesis, but the intermediate had the largest effect. Why? Because in the early 1 to 4 hour period, there were relatively similar levels of protein synthesis in the early hours of recovery, right? Pulse is maybe a little bit lower. But if we look at the amount of protein synthesis at those regular intervals, so 4 to 6 and then 6 to 12, the intermediate distribution maintained protein synthesis to a higher effect overall in the entire 12-hour period, right? Whereas maybe bolus was initially high, but then after that first 3-hour period, the absence of protein actually decreased, right? And then you were fed again, right? But by that point, maybe it had already decreased at that point, okay? So it wasn't as high over these other 2 extended time frames. The pulse distribution was not as high as the intermediate in terms of protein synthesis, and it never really got any higher than that, okay? So even though you were taking more protein here, okay, that protein wasn't being synthesized or incorporated the same way, right? It was too much all at once, and then it was so spread out that maybe it wasn't maintaining synthesis over a longer period. The pulse distribution, right, what I'll tell you now is that your muscle is refractory to amino acids, meaning, where have we heard the refractory period before? Right, action potential is the depolarization. Remember, when you have an action potential sent, each node of Ranvier depolarizes, and then it goes through a period of refraction, right? That refractory period is where you cannot further stimulate that neuron until a certain period has passed, right? So you can stimulate that node as much as you want, but it's not going to depolarize again until it's gotten to its resting membrane potential. It's refractory. So what this means is that refractory is that it can't be further stimulated, okay? So your muscle is like that with amino acids. And what they've shown is that if you have these transporters on your muscle cells, on the cell wall, that when amino acids pass by, it senses that. And it will grab those amino acids and transport them into the muscle. Right? Remember, your muscles have a cell wall. How do things get into them? Well, some, if they're soluble, they can pass a lipid bilayer and just come in, like steroid hormones, testosterone, estradiol, cortisol. They can easily pass through, right? But if they're proteins, they can't enter. They have to be transported in, okay? Certain hormones like epinephrine can't enter at all, right? So they work with a receptor and signal from the outside, okay? But amino acids have to be transported into the muscle. And how they do that is because there are these amino acid sensors that can tell the muscle when amino acids are present, and if they sense that, they will transport them in. What's interesting is that if the muscle cells are chronically and continuously exposed to amino acids and proteins, those sensors get desensitized, right? They get refractory. Once you've undergone protein synthesis and it senses more amino acids are present, if it keeps being exposed to that, they kind of stop sensing those amino acids, and also it kind of shuts down the responsiveness of protein synthesis, right? It's kind of like, a little kid in the candy store, mommy, 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 right? It's kind of like, okay, right there, you're right there. And like, okay, I just need to okay, stop for a second, right? So this kind of what happens here. It's a smaller amount, it's 10 grams, but if you're doing it every 45 minutes, it's being stimulated so frequently that at some point the muscle kind of desensitizes itself to those amino acids, right? It becomes refractory so that those amino acids, which normally stimulate protein synthesis, they're not stimulating protein synthesis now because it's not responsive to it as much because it's being exposed too often, too frequently, right? So in this case, smaller, more frequently, does not optimize the protein synthetic response, okay? And you might see some people like, oh, you take protein, it causes protein synthesis. That's true. Oh, I should take it more often. I have friends who will be walking around doing a protein bar all day long. Protein shake here, a lot of eggs here, protein bar here, and then they keep taking some a high protein waffle or something. I don't know, constantly taking protein all day to get their protein in. But the idea is actually taking protein so frequently, like every 2 hours, every hour, every 2 hours, is probably not working your benefit. Okay, so what they end up showing is that having a little bit longer distribution between feedings with a more moderate dose actually sustains more protein synthesis over the recovery period than less amounts more frequently or more amounts less frequently, right? So this is where the recommendation kind of comes from in terms of distribution. Now, 3 to 4 hours, that kind of falls in line with most people's normal feeding schedules anyway. You wake up, you have breakfast, maybe you drive to work, or you have a mid-morning snack maybe a few hours later, maybe you have lunch a few hours after that, maybe a pre-workout meal or pre-exercise thing, right, or mid-afternoon snack, exercise, take your protein shake, right, and then maybe have dinner a little later, or pre-sleep, something or something like that. So it actually 3 to 4 hours in between feedings for the administration of protein actually fits in most people's schedules, right? So there's not a need to feed way more than that. And in some cases, if we think about some diets like ketogenic diets or not ketogenic, intermittent fasting diets, where you're getting your protein in, but it's all in one sitting, right? In the other 12 hours, you're totally fasted. That long absence of the amino acids in circulation, that actually makes the muscle catabolic, right? The muscle senses there's no amino acids present, I'm starving, it shuts down protein synthesis, and then when you feed again, all that protein taken in one sitting doesn't get absorbed the same way, right? It's not as effective, right? It's kind of like maximizing that response, right? And the extra protein is just not really incorporated. So there is something to be said about also what type of diet you're doing and how you're trying to address that with resistance training adaptations. Yes.
What about if people are on the carnivore diet? Would that have an effect on their amino acid intake?
Yeah. So I mean, if you're on a paleo or carnivore diet, you're just eating meats, right? So if you're in a caloric deficit, then when you consume those protein should stimulate protein synthesis. However, they've also shown that some components of maximizing protein synthesis do depend on having other nutrients, other macronutrients. So, for example, they did a study a year or two ago where they had, when we think about eggs, where is the protein located in eggs?
No white.
In the whites, right? You get all the egg, white almond, all this, right? All the protein is in the egg whites. In the yolk, cholesterol and other nutrients, stuff like that, but the amino acids are not in the yolk itself, okay? So the idea was, let's look, people do resistance training, let's have them take an egg as a whole egg with the yolks included, or let's have them do just egg yolks. It's the same amount of protein, right? The amount of protein post-exercise was the same. The only thing that differed was one time they had the yolks intact, the other time they did not. What's interesting is that when they looked at protein synthesis, despite the fact it was the same exercise stimulus and the same amount of protein, the group that had the yolks included had a higher protein synthetic response. So there is something about having whole foods or nutrient-dense foods outside of just the macronutrient, like just how much protein or how much amino acids. There is something about this synergistic effect of having other nutrients included that promotes a beneficial response compared to just the amino acids alone. We kind of see this too, like they sort of thought, like, was it the fact that there was lipids and fats in the yolk that might have meant more energy available and that stimulated protein synthesis more? We do know that if you're on a diet, the caloric deficit blunts protein synthesis. So even though you take the proteins, right, and that does stimulate protein synthesis, overall, because you're in a deficit, it's a lower response compared to if you had not been in a deficit. So they kind of surmise, well, maybe it's having more calories from the yolk was more optimal, and that led to more protein synthesis, despite the fact they had similar protein amount, right? But it just goes to show that actually having a balanced diet and having, you know, sufficient macronutrients in your diet, or even, you know, don't just take, you know, food in isolation. I have some friends who, they don't even eat normal food. They're just worried about, what are my macros? Okay, I'm gonna have these carbs, and then I'm gonna make sure I get all my protein. I got chicken, I got steak, and then I have, you know, the rest of my protein's coming from supplements. And it's like, what about fish? What about grains? What about nuts, right? What about these other variables, micronutrients, vitamins that are part of a required healthy diet, right? You're missing out on that because you're just focusing on the one macro, right? So there is data to suggest that having a well-balanced diet with nutrient-dense foods is probably essential. And then if you already have nutrient-dense foods in your diet, then supplementing with supplements on top of that can enhance that effect, but just supplements alone are not sufficient. For example, leucine is the most stimulatory amino acid out of all of them, right? It's also a branched chain amino acid, so your muscle can use it for energy. There's a huge push in supplement stores, supplement companies to push BCAAs, more leucine, more mTOR activation, more leucine, more protein synthesis. And it really got out there that BCAAs were this like holy grail of supplements, when in fact, if you have someone just take BCAAs versus actual protein, just whole proteins, like full amino acid profile, the protein synthesis is better with the whole proteins, right? The BCAAs, even if you load more leucine on there, stimulates more mTOR, but it doesn't stimulate more protein synthesis, right? So, you know, the BCAAs can be good if you're in a like deficit maybe, or like you're highly active, but overall, just taking BCAAs or primarily taking BCAAs with some proteins is not the way to do it. It should be whole proteins, take whey protein, casein protein, whatever. You're not getting the whole picture just with BCAAs, right? Despite the fact what, you know, GNC and supplement companies and stores will push on you, BCAAs does this. You look on the back of the thing, this study showed this, and they have the bar graphs with this clinical trial showed this result, scientifically proven. When in fact, if you look at studies on just BCAAs compared to whole proteins and whey protein sources, overall there's a much better effect and adaptation with the actual protein source, much less with BCAAs. But if you look at BCAAs versus placebo or BCAAs versus carbohydrates in isolation, of course BCAAs is a better response because that is an amino acid, it's a protein. But compared to whole proteins, very different response, all right? So just a thing to keep in mind, because again, with like some diets and some supplements, you know, there are beneficial aspects of each diet, like you devise that diet for some reason, right? But every diet has pros and cons, just like where you're getting your macronutrients from kind of depends on that stuff too, right? So if you do take more protein, okay, you might say, but what happens to that protein? That 40 grams twice, that bolus distribution, it didn't result in more protein synthesis. So what happened to it? So if in this study they had people who perform resistance exercise and they had either no protein, 10 grams of protein, 20 grams of protein, or 40 grams of protein. And we looked at myofibrillar protein synthesis. If you had no protein, protein synthesis went up. We know that resistance training is anabolic, it stimulates protein synthesis. What's interesting, in this study, 10 grams did not increase protein synthesis more than no protein at all, right? So in this study, 10 grams was insufficient to see a difference there. Was the last study, 10 grams did increase protein synthesis, but it took a 12-hour period, accumulated over a 12-hour period. Here, just a few hours, 10 grams, not enough. 20 grams was significantly higher in protein synthesis compared to the other two, the 0 and the 10. However, 40 grams, although it elevated protein synthesis, 40 grams was not higher than 20 grams. So, if this is saying 20 grams significantly increases protein synthesis post-exercise, and 40 grams also stimulates, but it doesn't result in twice the amount of synthesis, then ultimately, we don't need to take 40 grams because that extra is not really causing an extra physiological response, right? So that's where the recommendations around why we should take 20, 25 grams after workout come from. It comes from data like this that looked at dosing and the responses. So they might ask yourself, well, what happened to that extra 20 grams of protein? Obviously it stimulated it, but it didn't create twice the synthesis. What happened to the other 20 grams? It was oxidized. When you looked at oxidation of amino acids, the highest oxidation occurred in the group where there was extra protein that was beyond what was sufficient for their needs, okay? So, you might have heard some of this, some myths out there that says, extra protein is turned to fat. Have you heard that before? Okay. If you're an exercising individual, if you have extra protein in your diet, right, and you're taking the extra protein after your workout, that extra protein is not converted into fat. The extra protein is oxidized and used for energy, okay? But if it's the protein that's being used for energy and not carbs and fats where you usually get the energy, then the carbs and fats become the extra calories, right? So it is true that if you have a diet that has a surplus of protein in it and you're an exercising individual, that you do have an accumulation of extra fats, subcutaneous fat. But if that fat is accumulating, it's not because of the extra protein. It's not the protein itself that is causing and becoming fat. It's the fact that it's now extra calories coming from protein would then mean the other substrates become extra calories. And we do know you can just store fat as fat, or you can convert carbohydrates into fat, right? And that's where the fat accumulates, right? In the post-exercise period, the extra protein is oxidized and used for energy. Now, if you're sedentary, if you're not exercising, high protein diets, that extra protein is converted into fat, right? So that is true, that extra protein is converted into fat, but that's only if you're sedentary, okay? Because if you're sedentary, what's the stimulus to tell the muscles to take up the amino acids and make proteins out of it? There is none. You're not exercising, right? But if you are exercising, the muscle does try to use that protein, and then if it's extra, it uses that as energy for oxidation in the recovery period. But then the other substrates become the extra calories. Yes?
So technically, let's say you're exercising and you're taking that extra protein. Could you then say that could be glycogen sparing?
It could be glycogen sparing, right? There is something that's you can make gluconeogenesis out of proteins, right? But realistically, it's a much harder process and longer process for that to happen. So if the body needed to use the glycogen immediately, it would just use it from the muscle anyway, because it would take much longer to actually get that carbohydrate source out of a protein background. It's possible, but it's probably not likely. So yes, that's where that comes from, right? So my analogy is like, when I think about this, the extra protein, if you have a bathtub, okay, you have the faucet that has the water going into the bathtub. Then you have the drain, right? The drain is where the water leaves, right? Think about your muscle the same way. You can add amino acids to the muscle, right? You consume it. The muscles then uptake those amino acids. They're inside the bathtub. They're inside the muscle. Then, if there's a stimulus, right, those amino acids get built into a protein, right? They go through the ribosome. They go through the drain, right? The synthesis is the drain, right? What determines the the speed that a drain drains water at?
That's the water's going.
How large are the holes, the pores in the drain? Larger holes, more water comes out, right? Smaller holes, the slower it happens, okay? So imagine if you had the rate of water going into the tub at the same rate that it was draining, what would happen? It would be level. Equal coming in, equal coming out. Your muscle, after you exercise, if the stimulus is sufficient, the ribosomes are already going to be maxed out in protein synthesis. They're working as fast as they possibly can. So if physiologically the muscle is already at maximum muscle protein synthesis, adding more amino acids to your circulation, into your diet, doesn't make the ribosomes do more protein synthesis. It doesn't make them work faster. They're already maxed out, right? So now those amino acids become extra, right? If we're talking about a tub, you add more water, what happens? If the tub is full, you add more water,
Excess water.
overflows, right? It doesn't get incorporated into the tissue. It doesn't get incorporated into the drain. It's overflow, it's extra, right? So that's what's happening post-exercise. These extra proteins and amino acids, they actually get oxidized and used for energy because they're extra. The ribosomes are already working at a maximum rate. So it's not gonna make them work faster. They're already limited, right? So that's where this concept comes in. It's also why the 40 grams, 2 times, that bolus condition, protein synthesis went up equivalent to the 20 grams, but it wasn't more, right? Why was that? Because the muscle was 20 grams for that workout was already enough. You can't stimulate synthesis any higher, right? We go back to that, right? Notice how they're all kind of around the same amount, right? This one is around there, this one's around here, this one's around here. This is around their maximum rate. They're not gonna get any faster than that. In this case, even though there was twice as much protein in this time frame, they were already at their maximum area there, the maximum amount. So you can't go any faster than that. So really that extra protein in this bolus condition was just extra, wasn't used, okay? Now, are there cases where you can take more protein? Yes, okay? A lot of those early studies, they did just knee extension exercise, they did leg presses, they did squats. Most of it was lower body only exercise, which was just one area. It happened primarily because when we studied muscle physiology, how do we study the muscle? You have to do a biopsy. The biopsies are coming from the VL. It's a very easy to locate muscle. There's a lot of muscle there. Not a lot of like nerve endings, right? It's pressure, right? Biopsies can hurt, but you're not going to significantly damage nerves there and so on and so forth. And it's a muscle that everybody studies. It's easy to get to. So a lot of them would do exercise programs that were just lower body or just lower limited muscle group activation of the VL. So the recommendations about 20 grams came from the fact that it was just a singular muscle group. The question became, well, what if you activated more muscle mass? All right, would you be able to use more protein? So then another study came out several decades later where they had them do whole body workout. It was a shoulder press, chest press, lat pull down, and lower body exercise. And they looked at when they consumed 20 grams of protein or 40 grams of protein. Well, in this case, when you did a whole body workout and activated more muscle mass, then you had higher protein synthesis compared to the 20 grams, right? So in this case, the extra 20 from the 40 gram condition, it's not extra, it is actually used, right? Imagine, remember that the tub example I gave you, right? You give them amino acids, it's making the synthesis in the legs, right? It's maximum amount. But imagine if you have another tub now, right? Now, if you have extra water, you could just put the overflow into the other tub, right? So if you're activating the upper body or other muscle groups, those extra amino acids can then be used in those tissues. So in that case, using more muscle mass or more various degree of exercise stimulus being activated in the muscle groups, you can use that protein in those cases. Okay, so how much protein do you need post-exercise? Well, it depends on the stimulus. If you're doing kind of a finite or controlled muscle group, maybe 20, 25 grams is enough, depending on your training status and the workout. If you're doing a whole body workout or doing a lot more muscle mass or a very, very rigorous type of workout, maybe you can go up to 40 and you'll be fine, but it kind of depends, right? So even if I did a bicep workout that was really, really hard, very small muscle group compared to other muscle groups, right? So even if it was a really hard workout, I need 40, No, 20 is probably good, right? 20 is probably good, right? If I just did lower body, but I did hamstrings and calves and squats and leg presses and a lot of volume and really, really tore up that muscle, hard workout, well then maybe I would want to go just beyond 20, 25 grams because it was a more rigorous workout. Maybe there's more damage, maybe there's a more stimulus there, but you wouldn't be doing it all the time. It kind of depends on what your training sessions are. And then lastly, a reminder that the workouts, your muscle is still sensitive to amino acids even 24 hours after the workout. So in this study, they had people do different exercise conditions, but they had them take a meal, right, on one day, and they looked at what was protein synthesis after the meal. And the other condition, they had them do the workout the day before, and then they had them take a meal and do the biopsies. And we can see that just having exercised the day before resulted in more protein synthesis compared to if you had not exercised the day before, right? So this means that your muscle is still sensitive to amino acid uptake and protein synthesis even 24 hours after the workout, right? So this is why I say the anabolic window is really much longer than we thought. Like, yes, 3 to 4 hours is fine, is good, but even if you don't get it then, the next day when you have breakfast, you worked out yesterday. The muscle is going to use that amino acids from breakfast way better at resynthesizing proteins compared to if you didn't work out, right? Because it wants to use that source to recover. Now, some strategies to enhance adaptation. Way back in the 70s and 80s, bodybuilders used to take protein pre-sleep because they thought, oh, I'm not eating in my sleep, right? I need to be anabolic, I need to be eating, right? So they thought taking more protein pre-sleep was a good strategy to enhance adaptation. And in fact, way back then, it did. That was a strategy that bodybuilders and athletes would use to try to enhance resistance training adaptations, because if you're not eating for 8 hours, but you have protein prior to sleep, maybe you can help recover the body better, right? They weren't doing the scientific studies to support that nutritional practice, but they know that it worked, right? Now, decades later, we can do these studies in the muscle and study protein supplementation and see, well, why did that work? It works because when you're, throughout the day, when you feed or you exercise, protein synthesis goes up, right? When you're not feeding or you're completely sedentary, right, or you start exercising in the workout, the synthesis goes down and the breakdown goes up, okay? When you sleep, it's called breakfast because you're breaking a fast, right? If you're sleeping, you're not eating, and so if you're having this situation where you're not active, you're not exercising, and you're not eating, you have these absence of nutrients which increases protein breakdown and suppresses protein synthesis. Bodybuilders would then take protein just prior to sleep in hopes that this anabolic stimulus of these amino acids would stimulate protein synthesis in their sleep. And they have done studies to show that when you take protein prior to sleep, it does result in better adaptations in muscle strength and muscle size, okay? Even if the groups have similar protein in their daily diet, just skewing the protein distribution a little bit towards at least having some prior to sleep can enhance adaptations. That's largely because in the sleeping period, right, if you have food or protein prior to sleep, that increases protein synthesis versus just rest alone. If you exercised, right, earlier that day, we know that exercise is a greater stimulus for protein synthesis, so of course, exercise is going to have a higher protein synthetic response in the sleep versus no exercise or just food. The best combination would be to have exercise earlier in the day and then also have protein prior to sleep, because now the muscle machinery is making the proteins because the response from the exercise, and you have the protein during the sleeping period to incorporate those proteins into the muscle and elevate it, right? Choice of protein here might be casein protein, right? Because you take it prior to sleep and it's going to digest very slowly and have a sustained level of amino acid in circulation supply, right? So that would be beneficial. The other thing is, you might say, well, should I do, how do I take my protein? Well, if you want 40 grams of protein prior to sleep, you gotta have 7 eggs, right? Or 2 chicken breasts, or 5 cups of low-fat yogurt, or 2 steaks, right? Yes, you can get the protein via whole foods prior to sleep, but I know that if I'm gonna have 7 eggs prior to sleep, I'm not gonna sleep. It'd be very uncomfortable, right? And who the heck wants to eat 7 eggs prior to sleep? I'm gonna like brush my teeth and go to bed. I'll be rolling around in my gut full of meat and eggs. It's easier, right, to get that amount of protein via a supplement, right? You could have in this case, 2 scoops of protein in low-fat milk can get 40 grams of protein in a small volume of meals, right? So this is a case where if you had to get more protein, it would be more efficient to get the protein via a supplement, right? You don't want all your macros coming from supplements, but if you don't, it's uncomfortable to cook and eat and all stuff just prior to sleep, having a protein shake is a much better and easier way to get those needs met, okay? So this is where taking a supplement, or a protein supplement, can be really effective in meeting your goals in a very time-efficient way. Now, if we look at the effects of diet, in this study they had looked at muscle protein synthesis. However, they looked at the skewing of the distribution of protein. So some people took their protein all at the end of the day. Other people took their protein evenly throughout the day. So all of these conditions, they were in a caloric deficit. And they look at the effect of being in a deficit with resistance training with the different protein distributions. What do we see in the energy balance condition, right? If you're fasted, right, there's pretty similar levels of protein synthesis, okay? If you're in the energy restricted state, so if you're on a diet, protein synthesis is depressed, right? If you perform resistance exercise in the diet phase, the restricted phase, resistance exercise in the fasted state does not increase protein synthesis. So if you know anybody who's on a diet and they do their workouts first thing in the morning without having food, essentially they're not stimulating protein synthesis. There's no adaptation happening, right? You're already in a catabolic environment. You're restricted in energy. So negative plus, not having the amino acids is also another negative. So overall that blunts this protein synthetic response. However, if you look at being in the fed condition, obviously in the energy balance phase, being fed, higher protein synthesis. In the energy restricted phase, just being fed is still suppressing protein synthesis, even though you've eaten. It makes sense because you're still in a restricted state, right? You're still in an energy inefficient availability, so of course synthesis is still suppressed. However, if you perform resistance exercise in the energy restricted state, so if you're on a diet and you lift weights, but you had food prior to that workout, you can increase protein synthesis to a level that is similar as if you were not on a diet, right? So from a muscle perspective, if you're on a diet, you should do your workouts in the fed state, and that can make the muscle protein synthesis increase to a level like you were not even on a diet. What does that do? That makes the muscle maintain protein synthesis and maintain muscle size, but because you're in a caloric deficit overall, you're going to be losing fat mass. You're going to be losing calories and fat there, right? So it preserves muscle mass, at the same time loses body fat. Mark?
What if you're not in a caloric deficit but you're fasted?
If you're not in a caloric deficit but you're fasted, the muscle is still catabolic. Yeah, so performing resistance exercise in the fasted state overall is a catabolic environment. The only way that it switches to anabolic is if you have protein post-exercise, right? So if you just worked out and then didn't eat for 6 hours, synthesis would never actually really even happen if you did it in a fasted state, because overall there's no amino acids present. Right?
But if you worked out fast, then ate after you eat.
Then you would be anabolic, yeah. And also, if you think elderly individuals need more protein compared to younger individuals, okay? So in this study, looked at maximum protein synthesis post-exercise in younger people versus older people. Older people needed twice as much protein to get the same protein synthetic effect. Why does this matter? Because elderly people already don't get enough protein in their diet as it is, all right? So if poor dental health, hard activities of daily living to cook the meat and eat the meat and all that kind of stuff, they're not getting enough protein anyway, and then whatever protein they are getting is not being absorbed in the same way as if they were younger. So I highly advise you to tell your elderly, grandparents, parents that they should have higher intakes of protein in their diet, because it's likely whatever they're getting now isn't sufficient for maybe how their body was responding to it a few decades earlier. All right. Now we'll switch a little bit in terms of carbohydrates. We do know that high intensity exercise relates to the preferential use of glycogen, okay? And it is important to remember that most times we're using glycogen in high intensity activities lasting at least an hour, right? So if you're over an hour and it's still high intensity, for sure we're going to be continually using carbohydrates because it's high intensity. Now, the amount of glycogen in the muscle is determined by how much carbohydrates in your diet and whether you did glycogen depleting exercise prior to the workout, okay? The more you deplete your glycogen, the less glycogen you have in the muscle, the less prepared you are for the athletic event. So it is important that if you're doing high intensity exercise, you need to be repleting and consuming carbohydrates in the recovery period so you can resynthesize the glycogen in your muscle. So the diet must have glycogen in it, carbohydrates in it. Now, this study shows what happens if you have two different diets and how it affects exercise to exhaustion, right? In this case, they had proteins and a diet that was mixed in macronutrients. They had proteins, carbs, and fats. They had one that was just proteins and just fats, and then one that was just carbohydrates. What we can see is that the diets that had no carbohydrates, so just proteins and fats, they had less glycogen in the muscle and they did not run as long, right? Versus a mixed diet that had proteins, carbs, and fats, they had more glycogen in the muscle, they could run longer. And then a high carbohydrate diet, they had the greatest amount of muscle glycogen prior to exercise, and that also meant that they could run the longest to exhaustion. So essentially what this means is that if you're doing high intensity exercise, something to exhaustion, you need a diet that has carbohydrates in it to have peak performance. Because if you have those carbs in your diet, you will have those glycogen in your muscle to use during your exercise stimulus, right? So this is why for athletes or people who are high intensity athletes, being on a low carb diet is absolutely detrimental to performance and adaptation, right? Because you literally don't have the substrate you need to exercise optimally. Now, when you take carbohydrates post-exercise, why do we need to get it sooner rather than later? Because unlike protein, where there's an extended window of synthesis, resynthesis of glycogen in the muscle happens in a much shorter time frame. So the resynthesis of glycogen from carbohydrate intake is going to be maximized because we have more permeability of glucose into the muscle. So because the muscle contracted, glucose can get in there a little faster and a little easier. Glycogen synthase activity is higher post-exercise, closer to the end of exercise. And then also the muscle is more sensitive to insulin. So all of these factors are going to allow glycogen to get into the muscle better, which means it's going to be able to be stored as glycogen more effectively than if we had waited longer, right? Once the permeability of glucose goes away because the GLUT4s have kind of gone back to the resting state, or the sensitivity to insulin's gone away, and glycogen synthase activity's gotten less because now it's 2 hours post-exercise versus 1 hour. All of those things mean that we can't synthesize and get that glycogen in and use it in the muscle because we've kind of missed our window there. Right. But optimally, you should have 1 to 1.5 grams per kilogram in the first 30 minutes. Sooner is better. And then also it should be high glycemic index foods, right? Because they're better able to be absorbed at a much faster rate. Right? Now, what happens when you have a high carb diet and you're not repleting your glycogen after workouts? Okay, we have a low carb diet, we have a high carb diet. The low carb diet is in the red, high carb is in the black. Similar amounts of glycogen prior to the exercise stimulus. After exercise, glycogen depletes. If you're in a high carb diet, you can resynthesize glycogen in preparation for the next workout. If you don't have carbs in your diet, you don't resynthesize glycogen. So prior to the second exercise session, this person uses glycogen, depletes. This person uses what they have, but is even lower, right? So then by the third workout, this person already had the glycogen in their diet, so they resynthesize back to their normal levels. They have enough to work out again. This one, they high intensity, deplete more glycogen, and that's it. So we can see that the more that we're not getting enough carbohydrates in our diet, the less prepared we are to have optimum performance in practice or repeated exercise sessions, right? Remember, the groups that had no carbs in their diet had less glycogen, did not run as far. So this relates here where if you're doing repeated days of training, right? Monday, Tuesday, Wednesday, you're doing high intensity that's depleting your glycogen, you need to get that glycogen in your muscle because you got another workout the next day. And if you don't, it's going to affect the quality of your workout in succeeding sessions, right? So getting the carbohydrates is important. Now, if you're in a high stress or, we talked about overreaching and overtraining just a little bit ago, if you're doing intensified training, they've shown that consuming a diet that's high in carbohydrates makes it so your mood is less disturbed, and you actually perceive that workout to be not as difficult. Okay, so notice here, in the intensified training with a high carb diet, their RPE was lower than the same workout with a low carb diet. So me as a coach or an athlete, if I know I'm doing an overreaching phase, or I know I'm gonna be doing some really tough training coming up, I need to make sure that I get more carbs in my diet, because number one, I need those carbs for the intensified training, and also it's gonna help me perceive that exercise session to be not as difficult, okay? So if we're doing harder training, but we're not perceiving it to be as hard, then ultimately that's gonna be beneficial for us psychologically and also from a performance standpoint, because we can kind of really do more work, but not really feel like it's more work, okay? Now, where did the low carb diets come from? There is data out there that shows, oh, if you are on a low carb diet, so if you deplete all your glycogen and you go to sleep without having carbohydrates, there's an increase in mitochondria, there's an increase in oxidative enzymes, there's an increase in capillaries from endurance exercise. So I'm sure, like, oh, you know, low carb this, low carb that, high fat this, high fat that. Like, why is that so prominent in endurance training circles sometimes, in those diets? Because if you look at the physiological adaptations to those diets and endurance exercise, there are beneficial aerobic adaptations. But those adaptations don't translate to improvement in performance, right? They're not gonna say gold, silver, bronze, okay? It just means you have more mitochondria, right? Or you have more capillaries. So despite the fact there being improvement in an adaptation, it doesn't mean that it translates to peak sport performance. Now here they had 3 diets. One was a high carb diet, one was a low carb diet, and the other was a periodized diet, meaning that when they worked out, they, in the recovery period, did not have carbohydrates. They just went to sleep. So they were in the depleted state. However, the next day, a few hours prior to the training session, they actually did consume carbohydrates that got into their system. So when they exercised, they had carbs available, but they did not have it in the recovery period, right? So they had carbs available during the training, but not in the recovery period. So it was periodized. What do we see? The low carb group actually improved their VO2 max. However, when you came to actual sport performance, so these were race walkers, when you actually looked at how fast they ran, the only groups that ran faster, improved performance, were the group that was high carb or the group that was periodized. The low carb group actually ran 2 minutes slower, right? They ran 2 minutes slower despite having an increase in VO2 max, right? So this is, again, showing, yes, you can have a certain type of diet that improves mitochondria, improves VO2 max, that doesn't translate to performance outcomes. Like, VO2 max is a marker of performance, but it's not necessarily indicative of sport performance, right? At least depending on the population you're comparing it to. In this case, having carbs in your diet, particularly high carbohydrates, is going to be more beneficial for adaptation. So more and more data shows that if you are an athlete, not having carbs in your diet is going to be detrimental to performance and adaptations. Repeatedly, they've done many studies to show that, right? Right, and then for women, we'll see that caloric intake is important in terms of thyroid hormones, right, and reproductive function. So thyroid hormones regulate metabolism, okay? And there's this concept of energy availability. And energy availability is the amount of energy needed for physiological functions versus the amount of energy also needed for activities of daily living and exercise. So if you are the energy that's normally used for physiologic function and maintaining reproductive physiology, in women, there's a competition for that. So when you're exercising more and not having enough energy available because you're exercising, then you get the suppression of the reproductive function in women, right? So you got amenorrhea, right? Absence of menstrual, of periods. You have oligomenorrhea, infrequent periods, right? And all that results in detrimental performance outcomes and health, really, okay? So Ann Laux was a researcher that looked at the effect of being in a balanced diet versus being in a deficit, and also the effect of low intensity versus high intensity exercise. And what she found was that it didn't matter if you were not exercising, low intensity or high intensity. If you were ever in a deficit, it resulted in a decrease in thyroid hormones, all right? And those drop in thyroid hormones affected metabolism, right? So we can see that they had the group that was on the deficit condition, lower thyroid hormones, lower growth hormone, lower glucose, higher cortisol. All those things are detrimental to physiologic function. And if you're an elite athlete, there are relationships between the loss of thyroid hormones and performance. So they had two groups. One was a amenorrheic athletes, so they had no menstrual function or they had menstrual dysfunction. Others had normal menstrual function. What we see is that when you had a drop in thyroid hormones, your reaction time got slower. When you had higher thyroid hormones, you had higher work output. Okay, when you had higher cortisol, you had lower work output. When you had higher cortisol, you had slower reaction times. So all this is to suggest is that these thyroid hormones are important for metabolism, they're important for reproductive function, they're also important for maintenance of adaptations and performance outcomes. All right? So that's all we got here. So we have, I guess we're not going to get to the alcohol stuff. So I guess we won't have that on the exam. But so yeah, that's pretty much that. So unless I can go over alcohol if you want, I have 2 minutes here. But well, actually we're out of time. But it's up to you guys. You guys have somewhere to go? Yes, you have somewhere to go. Yes. Okay. You guys go. So okay. So if you want, you can just review the slides. If you're interested in alcohol, I will take these questions off the exam, so they're not on that. You're not getting tested on that. And then I will see you guys for the final exam. So make sure you're on time. Make sure you have an 882E Scantron. Right? It's only 60 questions, multiple choice. So most students are done in about half hour, 45 minutes. It's not super long. Some students take longer. You actually have the entire 2-hour period to take the exam, right? So it's even longer than a normal period. But most students are done sooner rather than later. So I would suggest try to get here on time. That's pretty much it. I'll answer questions related to the exam up until Wednesday morning. Outside of that, that's it. Have a good semester, you guys, and I will see you next Thursday. And the exam's at 8 a.m., so make sure you're here at 8 a.m. in this room, okay? It's not 9 o'clock, it's 8 o'clock. All right, see you then.